In this video, we're solving problem 15.1.039 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to determine whether the field is conservative. And then it says, if it is, find a potential function for the vector field. If the answer does not exist, enter DME. So we've got a field. It has components in the x direction and y direction, and it's a function of two variables. So this is a vector field in R2, or a vector field in the plane. To determine whether a field in the plane is conservative, you need to identify the component functions. So if we have a field in the plane, we can write it this way in component form. Let's say that those component functions are labeled m and n. If the partial of this function with respect to y is equal to the partial of this function with respect to x, then the field is conservative. That's just the test. We go over why that's true in the videos that cover this concept more fully. Okay, so if I want to determine whether the field is conservative, I need to identify m and n and then take those partials and then see if they happen to be equal to each other. Now, this is written in a slightly different form. It's helpful here to remember this concept. Remember back in that first chapter when we studied vectors, we said if you've got a constant times a vector with components u1 and u2, multiplying by that scalar is done this way. You just multiply the scalar through the vector component by component. That's exactly what we have here. This is just written in terms of the standard unit vectors I hat and j hat rather than in component form. So this is the same as saying c times u1 times I hat plus u2 times j hat. And we would distribute the c here and here. Okay, so that will be our first step. So f is this, and I'm going to switch to component form because that's my preference. I've got 2y times this function, and we like to make our letters alphabetical for some reason. So it's 2xy times the exponential. And I don't know why WebAssign put that 2 directly in front of the y. I'm going to pull that out front. So we've got that. And then the y component is x times this exponential. X times that x out front gives us an x squared. So we distribute first, then we identify our m and our n. And then once you've identified m and n, go ahead and take those two partial derivatives. You're taking the partial derivative of the x component with respect to y. And you'll take the partial of the y component with respect to x. So I've got the partial with respect to y of 2xy times e to the 2x squared times y. And this is a product. I've got a function of y here and a function of y here. If this was just a function of x, I could treat it as a constant and I could just take the derivative of this and multiply it by the constant, but it's not. I've got a function of y times a function of y, so I have to use the product rule. This is my first function and that's my second function. Now, according to the product rule, the derivative of a product is the derivative of the first times the second, undifferentiated, plus the derivative of the second times the first, undifferentiated. Now over here, when I'm taking the partial derivative with respect to y of 2xy, I'm treating x as a constant. So this is really the derivative of a constant times y. The derivative of a constant times y is that constant, so I get a 2x right here. Now when I'm taking this derivative, I see e to some power, and that power involves y, but it's not just a y, it's a 2x squared y. So I have to use the chain rule. This is my inside function. The derivative of e to some power by the chain rule is e to that power. So you put your inside function back inside, and then you multiply by the partial derivative with respect to y of the inside. Again, you're looking at this, it looks like you've got a lot of variables, but try not to think of it that way. Y is your variable, x is being treated as a constant. So this is really a constant times y again. The derivative of a constant times y is the constant, and in this case, that constant is 2x squared. So we've got a lot of different pieces here, but now we want to write them all together. This is 2x times the exponential. And here I've got the exponential times 2x squared times 2xy. 2 times 2 is 4. X times x squared is x cubed. Bring the y down and bring the exponential down. So that's the partial of m with respect to y. We need to check and see if the partial of n with respect to x is the same thing. If so, the field is conservative. So we're taking the partial of n with respect to x, and n is the y component of our field. And so you're looking at this and you're thinking about the overall structure of it. Saying, what rule do I apply from Calculus 1 first? Well, I've got a function of x times a function of x, so I have to use the product rule again. According to the product rule, we get the derivative of the first with respect to x times the second undifferentiated plus the derivative of the second with respect to x times the first undifferentiated. And the derivative of x squared with respect to x is 2x. And the derivative of e to some power, where that power involves x, requires the chain rule. That's our inside function. Derivative of e to some power is e to that power times the derivative of the inside, treating x as our variable and y as a constant. So 2y is a constant. We could bring that down. And we multiply that by the derivative of x squared. Derivative of x squared is, of course, 2x. Okay, so now let's simplify all of this. I've got 2x times the exponential. And over here I have 2x times x squared times 2y. 2 times 2 is 4. X squared times x is x cubed. And then I've got a y. And I ask myself, are those two partials equal? And turns out that they are. So that means our field, our 2D field, is conservative. Now that is your test if F is a field in the plane. If F is a field in three-dimensional space, you have to use the curl instead. This is not enough to say that the field is conservative in 3D. This is our 2D test. Okay, so the question says, determine whether the field is conservative, and then if it is, find a potential function for the vector field. If the answer does not exist, answer does not exist. Okay, so we know it's conservative and we want to find the function, the potential function associated with this field. Now this is our test for conservative fields. It doesn't really tell you what the definition of a conservative field is. Let me write that down for you. A field is conservative if there exists a function f The way we write there exists in math is this little backwards E. And this is a field in as a function of two variables. It's a field in the plane, so this is a function of two variables as well. There exists a function little f of x and y such that if you take the gradient of little f, you get the field back. Okay, so that means, and this function little f, that is the potential function for the field. So you're trying to find the function f that you can take the gradient of to get the field back. Okay, so that's our next goal. You write down my field again. Whoops. So there's some function little f out there where I take the gradient of little f and I get this. And remember what the gradient of little f is. That's the partial of f with respect to x times I hat plus the partial of f with respect to y times j hat. So f is equal to this for some function f. And we're trying to find that. We're trying to find that function. Well, remember, two vectors are equal if and only if their components are equal. So the partial of f with respect to x must be equal to that. And the partial of f with respect to y must be equal to the y component. And we're trying to get f back. So what did we do? Let me write down our steps here. We set f equal to the gradient of little f for some function f. And we said that that implies that the partial of f with respect to x is equal to m, that's the y component, or the x component, excuse me, of capital F. And the partial of little f with respect to y is the y component of our field. So we set those equal to each other. Now you're trying to get f back. And we have these two derivatives. Well, to get rid of derivatives, we take antiderivatives. And we're going to do this twice. I'm going to try to figure out what f would have to be. So f of xy is the antiderivative of the partial of f with respect to x with respect to x. Here we are. And let's see, I'm taking an antiderivative with respect to x, and I've got a 2x out here and a 2x squared in here. I'm treating y as a constant. I think a u substitution should work. See a function of x inside another function. Remember, we're never really sure it will work until we compute du. If u is this inside function, du is the derivative of that with respect to x, treating y as a constant, times dx. And then I compare this to what I have up here. Now this says 2xy times dx. This says 4xy times dx. I'd really like that to be a 2. So I will divide both sides by 2. And so we've got that right there. So this becomes the integral of e to the u. And this 2xy times dx is 1/2 of du. The antiderivative of e to the u is e to the u plus what would typically be a constant of integration. Now we're working with functions of several variables. So this function is constant with respect to x, but it's not necessarily constant with respect to y. So we will say plus g of y right here. And of course, don't forget to back substitute. So f is 1/2 e to the u, where u is 2x squared y, plus g of y. So we've recovered f partially. We know it's this plus some function of y. Now to figure out what that function of y is, we're going to do the same thing with the partial of f with respect to y. We know that when we take the partial derivative of f with respect to y, we get this. And we'd like to get f back. To undo that differentiation, we'll use anti-differentiation. We're taking the antiderivative of the partial of f with respect to y with respect to y. And I've got this right here. Now, x squared is a constant, so you can bring that down. And this is a constant times y. I know it doesn't look like a constant times y, but that's a constant times y. Remember when we solve problems like this, when we take the antiderivative of e to the kx, we get e to the kx, and then we always divide by k plus, and then we add that constant of integration. We divide by k because when we take the derivative, we'd have to multiply by k by the chain rule. When we take the antiderivative, we're undoing that. So this is very similar, but this time instead of just a constant k, this thing that's constant with respect to y happens to be a function of x. So the antiderivative of e to the 2x squared times y with respect to y is e to that power. And then you have to divide by the k, divide by that constant. So we're dividing by that 2x squared. And then we add a constant of integration, or what would typically be a constant of integration. But this is a function of two variables. We're anti-differentiating with respect to y. We anti-differentiate with respect to y. We need a constant, or a function that's constant with respect to y, but not necessarily with respect to x. So I'll call that h of x. The x squareds reduce, and we end up with 1/2 times the exponential. Now at this point, we've got some matching to do. This is our field, or this is our potential function f, and this is our potential function f. So we need to put those two pieces together to get a single potential function. These are two ways of representing the same thing, and we want the whole thing. Unfortunately, this is saying it's this function plus a function of y, and this is saying the field, or f, little f, is this plus a function of x. So I write down whatever they have in common. I know f of xy has a 1/2 e to the 2x squared y term in it. And then I look at the part that they don't have in common. Those have to be equal to each other. This function of x has to be equal to this function of y. The only way that happens is if they're both equal to a constant. We'll call that constant k. So this is our potential function. Now, if you want to check, make sure this actually works out, let's take the gradient of that potential function and see if we get our field back. So we'll take the partial with respect to x, of f, and take the partial with respect to y of f, and hopefully, we get the original field. Derivative of e to some power is e to that power times the derivative of the inside with respect to x, treating y as a constant. Derivative of the inside here is going to be 4x times y, because y is a constant. Bring the 1/2 down. Derivative of e to some power is e to that power, times the derivative of the inside by the chain rule. The derivative of the inside with respect to y is 2x squared, because it's a constant times y. And then of course we can simplify the 1/2 and the 4. Multiply, give us a 2. We've got this right here, and that 2 times 1/2 is just a 1. And the question is that the original field? And it is. So that means you know that you've done everything correctly.